Welcome to Math with Marty. And we're back again. Last week we started off doing some calculations on the aqueduct and how much water flows to Winnipeg through the aqueduct. And in the course of the discussions, we brought forth the fact that in Winnipeg we use per man, woman, and child 500 liters per day of water, which is 1/2 meter cubed per man, woman, and child. And then I wanted to do some calculations to see what it would cost if we had to create our water artificially, in other words, to desalinate from seawater. And we did some calculations, and it turned out that just based on the naive or the stupid way of distilling water, which is to completely vaporize, let's say, a cubic meter of water and recondense it into the pure liquid, leaving the salt behind. The energy required would be the equivalent of 50 liters of gasoline. 50 liters of gasoline to vaporize 1,000 liters of water. In other words, 50 parts in 1,000, 5%. You try to convert gasoline to water, you've got a multiplication of only 20. In other words, how much water you need, am I trying to say this right? You need 5% of that amount in gasoline. Now, for one person, that would be 25 liters per day, because we use about 500 liters per person. 25 liters per day, which is $10 a day, which is an outrageous cost. That's a lot of money if you had to do it. But what I said at the end of that show is that it turns out that there's a lot better ways of accomplishing the desalination process rather than simply vaporizing the whole mass of the water and then recondensing it. And I want to talk about that today. Now, the whole key to the process is a matter of recovering the heat used to boil the water. Because just as sure as you put heat in to boil the water, when the water recondenses, it gives back the heat. And the only problem is the heat which it gives back, since you're normally recondensing it at a slightly lower temperature than you boiled it, that the heat available on recondensation is at a lower temperature, so you can't use it to boil the same stuff as you were before. Except there's a way around this, which is to boil at lower pressure. So the key here is to take your first stage and boil water at, let's say, 100 degrees centigrade at atmospheric pressure, and then condense it a few degrees colder, let's say 95 degrees centigrade, and use that condensing water at 95 centigrade to feed a second process where you're boiling water at 90 degrees centigrade. But in this case, to boil at 90 degrees, you've got to reduce the pressure. But presuming that you do that, you have water you're boiling at 90 degrees with the same heat you initially put in at 100 degrees, boiled, recondensed. Now you're boiling at 90 degrees, recondensing that process at 85 degrees. And then you'll take another vessel of water at still lower pressure, boil it at 80 degrees, recondense it at 75, etc., right on down the chain, and maybe you'll get 8 stages in like that if you go down to 20 degrees. So with the same 50 liters of gasoline, you've boiled a meter cubed of water 8 times over. So now you've got 8 meters cubed. And this is the sort of the simple way of trying to explain how the efficiency is improved. Now, this becomes, of course, a complicated process. It involves a lot of equipment. The heat transfer is a huge problem to get water to condense in one set of tubes at a certain temperature, and then you've got a tube, in other words, that the water is condensing at 95 degrees, so maybe it's only heating the tube to 90 degrees. And with a 90-degree tube going through snaking through a cauldron of water, you want to boil that at 85 degrees. So you've got very small margins. You know, when you put a heater in your coffee cup, the heater could be at 200 degrees centigrade, and you're boiling at 100 degrees centigrade, so you just need a little heater, because the heat is transferred into the water inefficiently. You don't need the efficiency, because you're just using the brute force of the high temperature gradient. But to accomplish a process like desalination economically, everything has to be done at the most efficient possible temperature gradients. And this doesn't begin to account for all the problems in the process. There's huge materials problems, for one thing, that you're doing all this boiling and condensing in an extremely corrosive liquid, namely salt water, within what kind of tubing. And you can only carry the process to a certain degree before the brine becomes so concentrated that it changes the properties and becomes impractical to boil it, so you've got to throw it out. There's a limit to how much you can boil away. Now, this is not a theoretical problem, because the stuff you're throwing out is warm. You can use the heat that you're throwing out to preheat the incoming resupply water. So there's some economics there, but it's, again, huge problem. There's a problem like if you're boiling at lower pressure. You reduce the pressure, you can boil at a lower temperature. But two problems arise. One, the volumes become much bigger. Boiling water at like 40 degrees centigrade, the pressure is probably only like a quarter of, it's probably only 10% of atmospheric pressure. So you're talking, the gas is occupying a much larger volume than it would at the higher pressures, necessitating much larger equipment. And worse than that, since you're operating at vacuum pressure, there's two problems. Air leaking in from the outside environment through any leaks in the equipment has to be removed, because it will fill up the low pressure volumes and occupy the heat transfer surface. Secondly, there's water. Water carries dissolved oxygen, which when you try and evaporate it, oxygen and air comes out of solution, filling up these vessels. All kinds of technical problems. But the point is, this multi-stage process is the basic idea of what's involved in trying to achieve economics. And you might also wonder, if you can boil at lower pressures, couldn't you also boil at higher pressures? And I think you can probably do that too. I think you could, and I've never worked in this industries where they do this kind of desalination stuff, but I don't see why you couldn't start your first stage at 200 degrees centigrade instead of 100 degrees centigrade. Now here you'd be at a much higher pressure. But if you start at a higher pressure, you can cascade it down that many more times. Now there's problems in this too. Okay, first of all, the gasoline that you're burning, okay, yes, the temperature is available to start at 200 degrees just as readily as 100 degrees. That's not a problem. But you get into very high pressures, you get into material problems. The corrosive properties of salt water is that much more aggravated at the higher temperatures. And there is an ultimate limit, because the critical temperature of water is something like 384 degrees centigrade, which is, first of all, the pressures at that temperature become greater than you can, in practice, handle with steel vessels and tanks and pipes. And second of all, beyond that critical temperature of 384 degrees, water no longer undergoes a boiling process where the change of phase from liquid to gas occurs through a boiling transition. The change becomes kind of a smooth, continuous process, which is almost impossible to visualize how that would even go. But once you get into that extremely high pressure and temperature region, you cannot any longer use this kind of boiling and recondensing to achieve the desalination. So there's numerous, engineering technical limits to what you can do. But I would guess offhand that a practical desalination plant would attempt to achieve a factor of 10 on our original 50 liters of gasoline per meter cubed of water, so that you'd be down to 5 liters cubed per cubic meter of water, which is per person, in the case of Winnipeg, 2.5 2.5 liters of gasoline, which is about $1 a day, which is getting down to where you could live at. My family of 5, what did that cost me? About $2,000 a year for desalinated water. Well, that's more within the realm of reason. It's interesting to consider what the absolute minimum theoretical energy requirement is. Of course, at the level we've gotten it down to, the equipment costs will begin to be outweighing the energy costs. So beyond a certain point, there's no point in trying to save energy, because the size of the heat exchangers and the boilers and condensers you have to build far outweighs the benefits. But it's a very interesting calculation to do the absolute theoretical minimum. I don't know if we'll have time for it today.
Well, whether or not you decide to do it, one quick question.
Okay.
Now, for every drop of water that we can drink out of this process, boils in each tank, or are the ratios funny? Is the water that you obtain to drink coming equally from the different stages?
Yeah, because the heat that you put into the first stage, you want to recover essentially all that condensing heat into the second stage. Now, it takes 540 calories to vaporize water at 100 degrees. And actually, it takes about 550 calories to vaporize your liter of water at 90 degrees. So you'll actually get a little bit slightly less water coming off the process at 90 degrees. But to an approximation, it's the same. It's the same. We should probably do a song about now.
All right.
And I thought it'd be nice to do something by Conway Twitty today. I'm a big fan of Conway Twitty. Conway Twitty, interesting thing is that he has played a large role in expanding the thematic scope of material available to the country music literature. Now, what do we mean by this? We know that there are certain recurring themes in the words of country music songs, such as trains, prison, cheating, drinking, etc. Did I leave?
Truck driving.
Truck driving, yes, CB radios, etc. There's certain solid kind of cowboy, any kind of cowboy theme is a valid country material. But in particular, religion, of course, songs about God. Now, however, in the arena of love songs, country music has traditionally had a different way of approaching it than rock music. Rock music has been sort of, hey baby, baby, you turn me on. It's been a very sort of a strong sexual base to the lyrics. Whereas country music has been more like, you know, darling, I'm sorry I cheated on you, and if you just give me one more chance, I know I can do you right, and this and that. It's a different idea, but Conway Twitty, as I was saying, has been one artist who has brought some of the more frank sexual aspect of love into country music songwriting. And one example of this was a song, Never Been This Far Before, which we're going to play for you. When it first came out, it kind of shocked a lot of country audiences, and I think it even got banned from the airwaves in some southern stations.
Well, let's hope we fare better on VPW 11.
I think Ona will put this one through. It's really quite tame by 80s standards. The stuff going on the other channels right now, you know, puts it to shame. But here it is, and this is what all the fuss was about. Never been this far before. I can almost feel the stillness as it yields to the sound of your heart beating. Bum, bum, bum. I can almost hear the echoes of the thoughts that I know you must be thinking. Bum, bum, bum. And I can feel your body tremble as you wonder what this moment holes in store. Bump, bump, bump. And as I put my arms around you, I can tell you've never been this far before. Now here comes the dirty part. Listen. I don't know what I'm saying as my trembling fingers touch forbidden places. I only know I've waited for so long for the chance that we are taking. I don't know and I don't care what made you tell him you don't love him anymore. And as I taste your tender kisses, I can tell you've never been this far before. And as I take the love you're giving, I can feel the tension building in your mind. And you're wondering if tomorrow I'll still love you like I'm loving you tonight. You have no way of knowing, but tonight will only make me love you more. Bum, bum, bum. And I hope that you believe me, 'cause I know you've never been this far before. Bum, bum, bum. Bum, bum, bum. Here we go. A big, big song for Conway Twitty. Doesn't sound all that shocking today, but it was a big deal in 1974, or whenever the heck. So, anyways, that's our little country music interlude for now, and we're going to go back to the desalination question. By the way, I did find some interesting figures on water consumption, and ordinarily the English language North American press is a very unreliable source when it comes to anything of a statistical, mathematical nature. You get these, I don't know, these journalism school grads who write articles about the economy or science and stuff, and they never put in enough figures for me to understand what's going on. But here's the little newspaper, the Canada Courier. It's the German language paper. And they got news from the homeland here, and a little story about water consumption in East Germany and West Germany, which says, "Waschen sich die Ostdeutschen öfter," which means, do the East Germans wash more often? And it turns out that since the unification of Germany, they found that while West Germany, the per capita consumption is 140 liters per day, in East Germany, it is 500 liters per day. And they actually don't attribute it to different habits of the people, but they say that they believe it is water, and I think I'm interpreting this right. Versickert der größere Teil des Trinkwassers im Erdboden. I think they're saying the water leaks into the ground before es den Wasserhahn den Verbrauchers erreicht, before it reaches the faucet of the customer. And I guess this is sort of a sign of the crumbling infrastructure of the communist East German economy. And I actually studied enough of this stuff that I can sort of understand half the articles, but I'm still kind of piecing it together. For example, the word faucet in this, which I'm interpreting Wasserhahn as water faucet, Hahn, H-A-H-N. I didn't know that word, but I actually picked it up on the very last page. You see, people say that the Germans don't have much of a sense of humor, but that's nonsense, because they have a whole page of the magazine devoted to extremely humorous anecdotes and little cartoons. And here's a little story of a family where the wife is on the phone and the house is full of water, and the husband is looking kind of embarrassed, and the caption says, "Es fängt damit an, dass ein Hahn tropfte," which means it began that a faucet was dripping. A Hahn, you see, they put the word Hahn. Und mein Mann ihn reparieren wollte, and my husband tried to fix it. You see, so the Germans really do have quite a sense of humor if you just sort of let them, let their hair down. But enough of that for today. I wanted to talk about the theoretical minimum amount of, and I'm going to go to the blackboard briefly. I haven't even made it there yet. I've been lazy behind my piano all day. And, okay. I had a little experiment that I once set up, and it went like this. Just to show something about water, I had a jar, and again, you cannot achieve this theoretical minimum in practice. But it's an interesting thing. I had a closed jar, and I put a little water in the bottom of the jar. And hanging from the top of the jar, I put a little container of salt, and I'll label it salt. NaCl, which we all know stands for salt. Thank you. And interesting thing happens. You know that if you take salt and water and mix them together, I've got to look at the right camera. These guys are going nuts here in the studio, but I'm going to try and be a good boy here for them. We know that if you mix salt and water together, the salt dissolves in the water. And in chemistry, we call this a spontaneous process. But just how spontaneous is it? The salt and water have such a powerful desire to mix together that the salts will actually draw water in from down below through the air. Water will evaporate from down here and condense into this little container of salt. And if the container is big enough, eventually all the water will condense into the salt. And funny thing is, how badly does it want to condense? It does want to condense because, look, it's going uphill to do it. So now we ask the question, how far uphill is the water willing to go, the fresh water, in order to dissolve in salt? How far uphill is the water willing to go? And the answer is almost unbelievable, how high it's willing to go. And for example, if this was ordinary seawater, because it's something that's sort of concentration dependent, if this was water typical of seawater, I will ask the question and maybe we'll discuss it next week. And we'll see what the answer is to this. And that's all for now. We're going to go back to the piano, just as Rob got the camera set up to do the board work here. You see there, the studio is all kind of topsy-turvy because they've been renovating it. We're going to have a big new look for VPW. We're going to put the Arsenio Hall show to shame with our glossy. We're going to have a band here. We're going to have a live studio audience. No, we're not going to have any of that stuff. But we do love getting fan mail. And Arsenio Hall never gets mail like this. Dear Marty, just wanted to drop you a line and tell you how much I love your program. Congratulations. Thank you. My husband, Brad, and I enjoy both the discussion and the music. Ironically, Brad was a math major and I was a music major, so this show is definitely for us. If possible, could you perform the song Never Ending Love on an upcoming show? It's our favorite. And that's from Claudette. Claudette, well, it just turns out that I happen to know the music, and Neil knew a bit of that song, and we're gonna try and do that song. And who did that song originally, Neil?
Delaney and Bonnie and Friends.
That's
but it's reappeared in recent years on the country charts. Performed by who, I don't know.
Yeah, well,
maybe
Claudette knows.
Claudette knows.
Yeah. Anyways, we don't know if you first heard it in the rock side of the station or the country side of the dial, but we're going to do it our own way. I have a never-ending love for you. From now on, that's all I'm going to do. From the first time we met, I knew I'd have a never-ending love for you. After being alone for so long, we can love one another, feel From the first time we met, I knew I'd have a never-ending love for you. Play it, Neil. Now sing with me. After all this time of being alone, we can love one another, live for each other from now on. Feels so good, I can hardly stand it. Never-ending love for you. From now on, that's all I wanna do.